Hey everybody, today we're going to be talking about convolution neural networks, also called convnets or CCNs, and then some other topics will include kernels, max pooling, and feature maps. This is the intro to convolution neural networks, and this is from chapter 5 of Deep Learning with Python by Francois Cholet. Okay, to begin with here, what I've done is, let me give you an overview of what I'm going to do today. I have written a little code that does a two-dimensional convolution, and then I'm going to show what a convolution does on an image, and then I'm going to relate that to deep learning and how we'll be using that within the Keras library itself. So I wanted you to get an understanding of what convolutions do to an image, and then start introducing how we will use them for machine learning. So let's get started. So the first thing that I've got here is pretty straightforward. I've loaded in the MNIST Handwriting library, and remember, this is just a load function once we've got the data loaded, and it's 60,000 training images and 10,000 test images, and we're going to look at a few of the training images. And remember that these are 28 pixels by 28 pixels. So what I've done here is say, okay, image number 35 is, let's run that and see if that is. That's a 5. It's labeled as a 5. That's the training label. And then the image is of a 5. And so what I want to do is introduce this idea of a kernel and 2D convolutions. And I'm going to use this tool to draw on my Jupyter notebook here. So let me kind of change this tool. So what a kernel is, and let's just spell out what I'm talking about. Kernel, and I'll use in other terms like a patch or a window, but let's describe what a kernel is. And really what it is a 3 by 3, and you can have a 5 by 5 or any size of a kernel, but a 3 by 3 kernel is really a patch or a small image that has particular values in it. And what we're going to do is do a dot product of this kernel and overlay it onto the image and then scan through the image. So our dot product may have something like zeros in it, or the kernel may have something like zeros in it, and let me just do a diagonal of ones, and we'll use this example in the future. So if I take that kernel and I overlay it into the upper left-hand quadrant here, upper left-hand corner, we will take that kernel and then we will start in that upper left-hand corner and we'll move through the image, and we'll move over a stride, in this case, of 1, meaning 1 pixel, 1 pixel. So we're going to do the dot product. If it's perfectly aligned with that upper left corner, the upper left-hand corner of the original image times 0, the next pixel over times 0, the next pixel over times 1, and then we'll dot product, so that's the element by element multiply, and then sum, and then replace the center pixel in our kernel with the new value. And so we'll learn a little bit why this is a particularly important type of operation, because what it allows us to do is, if you can imagine, if we had underneath the image a perfect diagonal of values, let's say 100, 100, 100 as pixel values, and we have that diagonal, that would give us the maximum. And so what it's just done is identified this particular feature in the image. All right, so that's some nomenclature, a stride, and then often you also see the term padding. And so if you think about it, if I took my original kernel and put it perfectly in the upper left-hand corner, and then replaced the middle value of the kernel in the original image, then I end up with a border that has no values. So often you'll see a term called padding, and all it means is I've added a padding of 1 pixel, so that if we start, and I may add zeros, padding all the way around, if we start our calculation, our kernel calculation, I replace then the upper leftmost corner of the original image data with the new value. So that's what padding is. Okay, so let's kind of get back to our code a little bit. So let me clear this here. Let's delete that and close it off. and run a little bit of this code and see how a 2D convolution image actually works. All right, so I've got image number 35 defined. And a typical image processing kernel will look something like this. I've got negative values across the row, and then I have an 8 in the center pixel, negative values across the third row. And this is a 3 by 3 pixel. So let's run that. If we were to run that, I've already run it, it would end up with an image here. So notice that it's kind of aggregated all the values, and if there was a value in the centermost part of the kernel, it really accentuated that. So you see that within the image. So it's a feature detection image. Now, what we want to kind of look at here is an example of maybe finding a 45-degree angle in the image. So let's change this code. Let's just remove this. Notice that I've got the variable kernel set up, so when I run this, this kernel will overwrite the one above it. So let's rerun that on this 5 image and see what that looks like. So notice it's highlighted the vertical, or not the vertical, the diagonal in the letter 5, right? So this is kind of vertical here, so it didn't highlight it as much. So you can see that highlighted in the image. That's kind of interesting, right? All right, notice what the kernel looked like. It was a vertical, 45-degree vertical from the lower left to the upper right. And then in the next case, I want to run a kernel that is a vertical line. So it's gonna, this kernel will identify all the vertical features. Now notice there's not a lot of vertical features in that 5. So let's rerun that. And we can see that it kind of got that part of the 5 and a little bit of that, but accentuated those particular features in the image. All right, for the last thing here, I'm going to implement a border, what I call a border kernel. It has ones around the edge. Now notice this is a 5 by 5. It's not a 3 by 3, so this is called a 5 by 5 kernel. And it's kind of an unusual kernel. I just made it up. So can you guess what's going to happen to the image? Now it's larger, so it's going to aggregate, do a dot product over a larger area. And you can see that when we implement the function, it kind of washes it out, kind of smooths it out. So that's another example for you to kind of play with. Now, here's the code for my Convolution 2D. This is not what we're covering today, is this code, but I wrote some code to be able to do that. Notice that I set a padding. I could have set the padding. I put padding of 0, so I really eliminate the first or the border pixels because I'm not using them. So the output image is 1 pixel less in the width and the height. And then I'm using a stride of 1. Now I could have used a stride of 3 or 5. Our images are only 28 by 28. And why you would use a stride is you might want to reduce the amount of computational load in the image. And your features are large features, something like that. So that's a way for you to optimize the performance of your code. So there's some 2D code, 2D convolution networks. Now, here's the language as it applies to machine learning. Here's the example from the book. I did something similar, but wrote the code for it. That's a 4. Here it shows how a single filter will highlight that particular filter or kernel's code. And here's some of the language, right? So we're starting with an original image, and then the output from the image with the kernel applied to it is another image. It's often called a feature map. So that's the feature map. In our case, we had a 28 by 28. We applied a 3 by 3 kernel, and if we do that in the code, we might do that multiple times because we want to learn multiple features. So what often you see in CNN models is you start with a large feature, you apply a lot of different feature of kernels, 32, 64, 128, because you're trying to identify a lot of different features. Now, as opposed to what's happening, what I just showed you, where you define the kernel and you look for them, what happens if you use a cost function is that what the neural net is doing is defining the kernels, the weights in the kernels, so that to optimize the classification. So you don't set the kernels, you don't set the kernel weights, the model automatically finds those for you. So what you end up with is a feature map stacked with several different feature maps depending on the kernels that you're using, and the number of kernels. And we'll go through an example of that in just a second. And so at the high level, you can think of these kernels as looking for specific features. For example, in a cat image, if we're looking at the ear, maybe looking for that triangle tip, which is different than what's in a dog. And through training and the cost function, then optimizes the weights for the kernels. So that to me is kind of a more intuitive feel for how neural nets work and how machine learning works, is that these kernels are identifying specific features. And so depending on how you design your model, you can have different layers in your neural network that are looking for different features at a very granular level. So here's an image from chapter 5. And so let's talk about this a little bit. So I'm going to come in here. So this is a sequential model. And let's go over some of the features here. Oops, let's do this. Okay, a little bit smaller. And so if we were to look at the model itself, so once again, this is a sequential model. And then the first function in our model is a convolution 2D, and it's conv2D. And then 32, the 32 here, is the number of kernels, which results in 32 feature maps. All right? So it's exploded the amount of data. We're going to start with an image that's 150 by 150. Oh, and by the way, this is an RGB, so there's 3 channels. So R, G, and B, those are called channels. So 3 channels, right? So here's some more nomenclature for the model. So we start with an image. We have 32 kernels. So the output of that is 32 images of 150/50. So there's this next function called maxpooling, which is an interesting function because it has its use is to reduce the size of the images. So we're going to go from, if we use 0 padding, we're going to go from 148 actually, 148. And then if we use max pooling, it's going to do this. It's a 2 by 2. And then let's say that in our 2 by 2 we have 0, 1, 2, 3. What it's going to do is it's going to take the max value that's underneath the max pooling window or patch and place that in the upper left hand corner here. So essentially what it does, it reduces the image by a factor of 2 in the height and width, because we're going to take 2 by 2 and then place the max value in the upper left hand corner. So its result is going to be a 74 by 74. Okay. Feature map. So that's what max pooling does here, right? And then in the next operation, we do a convolution 2D network, and it has 64 kernels, or 64 feature maps with a 3 by 3 kernels. And then the next function, we do a max pooling. So if we do something kind of interesting here is we can go and we can do the calculations on the number of parameters, which is the number of weights and biases. And this becomes important in understanding how to optimize your model for performance, because if you have very large kernels, you end up with 7 by 7, and you have if you don't do max pooling, and you do a lot of different kernels, let's say you do 128 kernels, you end up taking your image, if it's a grayscale image, and multiplying the number of images by 128. And if it's RGB with 3 channels, it's 3 times 128. So this becomes important in actually optimizing the performance and in your compute power and memory. So let's do a little example here of how to calculate the number of parameters, or the weights and biases. So let's adjust the size of our pen just a little bit. And so we can now come over here and say, okay, so the kernel size we've said is 3 by 3. We have 3 channels in this. We have RG and B because it was a color image of a cat. And then the pixel size is 150 by 150. All right. So, and then we have, and for the convolution 3D, the first layer here is the output. The number of feature maps, the number of kernels is 32. So if we did the calculation, we would do 9 times 32 times 3 plus 32. So 9 times 32, 9 is the kernel size, 32 is the number of feature maps, times 3, which is the number of channels. That gives us our weights, right? It gives us our weights, and then we need a bias for each kernel, and that gives us a bias here. So this is the weights plus the biases. And that is equal to 896. All right. So that's how you calculate the number of parameters. And notice that after we do a max pooling to reduce the image size to the feature map to 74 by 74, and it had 32 output channels, but in the next function, we're going to take the feature maps and explode it to 64. And what that essentially does is takes the original, so we take the original number of features times the kernel size times the output number of feature maps plus the biases for the feature maps, and now we have a really large number of weights and biases that we're calculating. It's 18,496 weights and biases. So if you take this one step further, maybe simplify and think of it this way: is I had a grayscale image, very simple, our MNIST data set. It's 28 by 28 pixels, and you think of the kernels conceptually as one kernel is the diagonalness. I don't know if that's a word or not, or horizontalness or verticalness, and I have 32 channels of that. So the weights is equal to the number of kernels times the kernel size, 3 by 3 in this case, plus the biases. So for an MNIST, with these number of attributes in a convolution network, we'd end up with 320 total parameters. So a lot less than with the grayscale, with the color image of the cat. So, and finally here, just to further go over an example of what max pooling does. So if we have an image that's 148 by 148, this is our CAD image, and we do max pooling, and max pooling does a stride of 2, because if it went over one value, it would replicate some information that's already in the max pooling window. So it goes by a stride of 2, and then reduces. Its purpose is to reduce the data by a factor of 2. If you have a max pooling of 2, now you could use other max poolings of 3 or 4 and so forth, but that's the objective of the max pooling, is to reduce the feature map, and what you end up doing is increasing the number of feature maps by defining more kernels. And what the cost function and what happens in the neural network is that those kernels are automatically optimized with the training data, so they're calculated within the model itself. So you don't define the kernels, they're calculated for you. So that's my introduction to convolution neural networks, concepts, and some key terms that we covered was max pooling, kernels, also called patches, and then channels, which is RGB, parameters, which is the total number of weights and biases. And this is a function called model summary. You can output the summary and look at this for your code. And so I think getting a good grounding and good handling on some of these basic concepts is really important to understand convolution networks. Okay, thanks. Until next time.